This lesson reviews the transformations you already know and thinks about some new transformations in different ways. So let's start off with a base graph of y equals x, y equals absolute value of x. This base graph is right here. And you should already know the basis because of shifting. So if you put a number after the x, like if I were to write y equals absolute value of x plus 2, it would take every point on the graph and shift it up 2. If I were to put the number inside with absolute value, like absolute value of x plus 3, it would take the entire graph and shift it to the left 3. And if I were to take something like y equals absolute value of 2x, it would make the graph steeper. So it would be like, instead of being over 1, up 1, the old point, it would be, the old point of 1 would go up to 2. And whereas the old point was at 2, 2, it would double in size, it would become 4. And so the new graph would be a steeper version of the first one. So you call this one the base graph. This number right here shifts it up or down depending on whether it's negative or positive. The number inside here is a little bit trickier. You have to look and ask yourself what makes it equal to 0, and that's how far you go to the right or to the left. So in this case, a negative 3 would make it equal to 0, so it moves to the left 3. And this number can make it steeper or less steep, and there's going to be a difference on whether it's in front of the absolute value or inside, and we'll talk about that shift in a couple of slides. So let's take a new base graph, y equals the square root of x. If you have a negative sign in front of the function, that's going to take the graph and it's going to reflect it across the y-axis. So negative square root of x would reflect this way. Sorry, I said that wrong. It reflects it across the x-axis. This negative here makes the graph go upside down. But if I were to, instead of putting the negative outside the function, put it inside the function, this transformation is going to reflect it across the y-axis, over y-axis. So the graph that originally went this way is going to instead, let me erase that, instead it's going to go the other way. So a negative sign reflects it over the y-axis when it's inside. Up here, the negative sign makes it upside down. So depending on where the negative sign is, reflects over the y-axis, turns it upside down. That's all old news. Now we're going to look at a couple of other things that you didn't cover in depth in Algebra 2. So in the next example, we're looking at how a 2 in front is different from how a 2 is inside. If I put the 2 in front from the square root of x graph, what's going to happen is in the first point right here at 1, 1, it's going to get twice as big, and so the 1, 1 is going to come up here at 1, 2. And the second point we plot, 4, 2, is going to get twice as big, and so it's going to be over here at 4, 4. So this makes all the y's 2 times taller. And so we usually call a graph like that a vertical stretch. And if that number, instead of being 2, if let's call it a, if it was y equals a square root x, if this number right here were less than 1, then it would shrink it. So when the number is in front, it's a vertical stretch or a shrink. Now on the next example, the square root is inside. And so in this case, when I take a look at the table, I still have a point at 0, 0, 1 is at 1.4, 2 is at 2, 4 is at 2.8. So it does get stretched a little bit, but it doesn't get stretched as much. But we don't refer to it as a vertical stretch, we refer to it as a horizontal shrink. And when you think about horizontal shrinks, think about like a couch. If you were to like stuff more people into a couch, you would have to scoot over and you'd have to like make your arms tighter. So like by the time I have a whole bunch of people sitting on a couch, everybody has their arms tight into them. And so it's kind of like they're getting skinnier. All these people stacked up on a couch, but not stacked up on a coach, sorry, stacked up on a couch. So a horizontal shrink is like stacking people on a couch because they have to scooch together, so they're kind of getting smaller and skinnier, but they also are scooting over at the same time. And I'll show you an example of that on the next slide. So here's an example of horizontal shrinking. Here's our base graph, y equals absolute value of x, with points at 1, 1, and negative 1, 1, and positive 2, 2, and negative 2, 2. So if I were to add in this shift right here is going to move the whole graph to the left 1. And so it's going to start here. And then this 2 right here is going to do what's called a vertical stretch. And so it's going to make everything twice as tall. So the point that's at 1 over here on this first graph is going to be 2 high on the second graph. And the point that's over here at 2 on the first graph is going to go 4 high. So the point that's over 2 is going to be 4 high. It's going to be up here. And so this graph has a shift to the left too, and it has a vertical stretch. Now let's compare that to a horizontal shrink. So this is more like the couch problem. When I look right in here, the 2 affects what makes the inside of the equation 0. And so if I were to ask myself, well, what makes 2x plus 1 equal to 0? I would have 2x equal to negative 1, and I would have x equal to negative 1/2. And so the vertex of this graph is actually at negative 1/2. And then this 2 is still going to make everything twice as tall. So if I go over 1, I have to go up 2. And I want you to look at this graph here and compare these two graphs. In the vertical stretch graph, it just started here and it got stretched. So it just sort of the whole graph got pulled up. But in this graph over here, it's like it's getting pushed sideways. It's still getting narrower than the original graph. Here's the original. This graph down here is narrower than the original, but it also got pushed sideways. And that's why the horizontal shrink is kind of like the couch, because when you're getting squished sideways, you're still getting skinnier, but you're also getting scooted over at the same time. So those can be a little more unusual to figure out, and it's always okay just to plot points if you're not sure. Next, we're going to look at compositions with absolute values. So in our first problem, our base graph is the parabola shifted down 4, and so it's got a point at negative 4 and at over 1 up 1, over 2 up 4. There's our base graph. Okay. So I want you to, before we go ahead and do this, to look at this graph right here and imagine that all of the graph had to be positive. So it's kind of like no negatives down here. And try to think to yourself what would that would look like. And so stop and think about that. So if I were going to make that whole graph positive, these 2 points right here, they couldn't go below, so the graph would come down. It would then get bounced back over into the positive region and go back up. So taking the absolute value is going to cause a reflection of this part of the graph, and this part of the graph gets bounced back into the positive section. So absolute value makes things positive. It also bounces graphs positive. Now, This transformation is going to do absolutely nothing, because when you square something, it's already positive. And so it will stay and look the same as it would before. So for the most part, it should be a pretty easy lesson. You just need to work on remembering all your transformations and doing your transformations without the use of a calculator. You can check your graphs afterward, but on the actual test, it'll be no calculator for transformations. Have a good day.